Have you ever wondered what makes the electricity in your home different from the electricity in a battery? The power from a battery is called direct current, or DC. This means the electricity flows in one steady straight line, like water flowing gently down a river. It's simple and predictable. We can use basic math to figure out things like voltage and current, but the electricity in our homes is different. It's called alternating current, or AC. In AC circuits, the electricity doesn't flow in a straight line. Instead, it constantly changes direction, moving back and forth many times every second. This constant change makes things a little more complicated. This back and forth movement is incredibly useful. It's why we can send electricity over very long distances, from power plants all the way to our houses. But it also means our simple DC math doesn't work anymore. Imagine trying to describe a swinging pendulum with just one number. You can't. You need to know how far it swings and how fast it's moving. It's the same with AC circuits. The voltage and current are always changing. They go up, they go down, and they switch directions. We need a new, smarter way to describe and work with these constantly shifting values. The way that voltage and current change in an AC circuit follows a very specific pattern. It's not random. It's a smooth, repeating wave. This wavy pattern is called a sine wave or a sinusoidal waveform. Think of the gentle, rolling waves you might see on a calm ocean. The voltage rises smoothly to a peak, then falls smoothly back down, crosses the zero line, and drops to a low point before rising again to repeat the cycle. The current in the circuit often follows a similar wavy pattern. This wave-like behavior is the key feature of AC circuits, and the reason we need special tools to understand them. So how do we handle these waves? If we tried to add or subtract them directly at every single moment in time, the math would get very messy and take forever. We would have to look at an infinite number of points along the wave just to solve one simple problem. This is where our new tools come in. Instead of looking at the entire wave all at once, we are going to find a clever way to capture its most important information in a simple snapshot. This snapshot will tell us everything we need to know about the wave's size and its timing, making our calculations much, much easier. Let's turn those complicated waves into something much simpler. An arrow. This special arrow is called a phasor. A phasor is a fantastic tool because it can represent an entire AC wave with just two simple pieces of information. First, the length of the arrow tells us the size or magnitude of the wave. A longer arrow means a higher voltage or a bigger current, just like a bigger wave in the ocean. A shorter arrow means a smaller voltage or current. This gives us a clear visual way to see how strong the electricity is in our circuit without having to draw the whole wavy line. The second important piece of information is the direction the arrow is pointing. The angle of the phasor represents the wave's position in its cycle, which we call its phase. Imagine our arrow is spinning around in a circle, like the hand of a clock. As it spins, the height of its tip traces out that perfect sine wave we talked about. By freezing the arrow at a specific moment in time, usually at the very beginning, when time is zero, its angle shows us where the wave starts. This is incredibly helpful when we have more than one wave in a circuit, like a voltage wave and a current wave. Now, let's think about why this is so useful. In many AC circuits, the voltage and current waves are not perfectly in sync. The current wave might start a little bit after the voltage wave or maybe a little bit before. We say they are out of phase. If we were just looking at the wavy lines, it would be hard to describe exactly how far apart they are. But with phasors, it's easy. We just draw two arrows. The angle between them shows us the phase difference. If the arrows point in the same direction, the waves are perfectly in sync. If there's an angle between them, we can instantly see which one is leading and which one is lagging. So, a phasor is like a snapshot of a spinning arrow that represents a wave. The arrow's length is the wave's peak value, its amplitude, and its angle is the wave's starting point, its phase. Instead of dealing with tricky wave equations, we can now work with these simple arrows. This turns difficult problems about waves into much easier problems about geometry. Adding, subtracting, and comparing waves becomes as simple as figuring out what happens when you put arrows together tip to tail. This visual trick is the first big step to mastering AC circuits. Using arrows is a great visual trick, but how do we do the math? Drawing arrows and using a protractor for every calculation isn't very practical. This is where another amazing mathematical tool comes to our rescue: complex numbers. You might have heard of them in math class. They sound complicated, but they are the perfect language for describing our phasors. A complex number has two parts, a real part and an imaginary part. Don't worry about the name imaginary, it's just a label for a number multiplied by j. Engineers use j instead of I to avoid confusion with current. Think of a map. To find a location, you need two coordinates like 3 blocks east and 4 blocks north. A complex number works the same way. The real part tells you how far to go along the horizontal axis, left or right, and the imaginary part tells you how far to go along the vertical axis, up or down. This two-part system is a perfect match for our phasor arrows. The horizontal position corresponds to the real part of the complex number, and the vertical position corresponds to the imaginary part. Every phasor can be described by a unique complex number. Now, the real magic happens. All the things we wanted to do with our wavy sine waves, like adding them together to find a total voltage, can now be done using simple arithmetic with complex numbers. To add two voltages, you just add their complex numbers. You add the real parts together and you add the imaginary parts together. That's it. What was once a very difficult trigonometry problem becomes a straightforward addition problem. This is a huge breakthrough. It takes the complexity out of AC circuits and lets us use basic math rules we already know. This connection between phasors and complex numbers is the key that unlocks AC circuit analysis. A voltage that is, for example, 10 volts at an angle of 30 degrees can be written as a complex number. A current of 2 amps at an angle of negative 15 degrees can also be written as a complex number. Once they are in this form, we can use them in Ohm's law, just like we did in DC circuits. The rules are slightly different because we are dealing with complex numbers, but the process is fundamentally the same. This method makes solving for unknown values in a circuit incredibly systematic and far less prone to error. Let's see how this works with a simple practical example. Imagine you have a circuit with a resistor and an inductor connected to an AC power source. The power source provides a voltage, and we want to find out what the current is. In a DC circuit, this would be easy. Just use Ohm's law, V equals 1 times R. In an AC circuit, the inductor causes the current wave to lag behind the voltage wave. This creates a phase difference, and our simple Ohm's law doesn't quite work. But with phasors and complex numbers, we can handle it with ease. First, we represent everything as a complex number. The voltage source has a magnitude and a phase, so it becomes our first phasor. The resistor's opposition to current, its resistance, is just a real number. But the inductor's opposition, called reactance, is an imaginary number. We combine the resistance and the reactance to get a total opposition called impedance, which is represented by the letter Z. Impedance is a complex number that tells us not only how much the circuit resists current, but also how much it shifts the phase. It's like resistance, but for AC circuits. Now we can use a new and improved version of Ohm's law for AC circuits. V equals I times Z. All three variables, voltage, current, and impedance, are complex numbers or phasors. If we know the voltage and the impedance, we can find the current by rearranging the formula to I equals V divided by Z. The calculation involves dividing one complex number by another. While that sounds tricky, it's a standard procedure that a scientific calculator can do in an instant. The answer we get will be another complex number, which represents the phasor for the current. The final answer, the complex number for the current, gives us everything we need to know. We can easily convert it back into a phasor to find its magnitude, how many amps of current are flowing, and its phase angle, how much the current is lagging behind or leading the voltage. By using this method, we have successfully solved a complex AC circuit problem without ever having to draw or add sine waves. We turned a tricky wave problem into a simple algebra problem. This powerful technique is what allows engineers to design and analyze everything from the power grid to our electronic gadgets.